Hello everyone, thanks for watching this video. I'm Nannan Wang and I will present an automated tool for detecting malicious NPM packages using behavior sequence knowledge mapping. JavaScript is the most widely used programming language, making its software supply chain security crucial. Recently, there have been significant security issues in the NPM domain, such as the packages mentioned here. Currently, some security personnel mainly use some features and classifiers to categorize NPM packages, and subsequently generate reports to deposit in security database by manual check. Further, they notify the official to remove or unpublish the packages. However, there are two main problems. The first is the scope of analysis is inappropriate, with many detection efforts focused on all JS code while ignoring fail entry. The second is that the classification results are poorly interpreted and often do not give an adequate behavior sequence. Let's consider a few examples. For a JS package, its functionality and usage are often reflected in its installation and import process, which contains some automated aspect, so we focus our detection on these processes. Consider this package as an example. On the left is its configure file, and on the right is its malicious code and commands. As a configuration file, many of its fields influence the package behavior, such as pre-install under the script field, which executes commands before the package is installed, leading to malicious behavior. After installation, users need to import packages first to use it. Index.js is an entry file for the package, and it will execute automatically when the user calls it. In addition to the main file, we also pay attention to bin, import, and so on. For behavior interpretability, we try to explain it to use a clear behavior sequence on command or code. Here we use the package as an example. As you can see, the config file here specifies index.js as the entry file, so subsequent behavior sequence will start from it. Analyze the API call, we can see the code first uses the OS API to get the host name. Next, it constructs a package that contains system hostname data. Finally, it sends the package to suspicious external address via the post method. Thus, the information threat was accomplished. In addition to the above analysis against the JS code, we can see that the package also executes a malicious command via the command execution API, which creates a reverse shell. Therefore, for effective malicious package detection, our research goals are: first, conduct a targeted and comprehensive analysis; second, build a classification framework; third, achieve an automated detector. To classify NPM packages more reasonably, we design a hierarchical classification framework consisting of 3 layers. The first is focused on malicious package categories. After reviewing some existing and manually analyze many packages, we summarize the following 5 categories. Then we classify behavior types according mutually exclusive and complete design guidelines. More specifically, we classify them into type and subtype, where subtype is mainly based on type due to the differences in the object it targets. For example, file read behavior type includes file read system info, file read sh info, and other behavior subtypes. In the third layer, we take the native API as the core and divide it into different API operations, 806 in total. For example, file read operations includes the following API calls: fs promise, fs file handle. Next, we describe the entire detector. First, we construct a local cache to obtain daily updates and historical malicious packages. Additionally, the local cache can aid in the subsequent detection of the in-the-wide packages. Then we build a code reconstructor to separate the commands to be analyzed from the code, and merge the JS code into one file for subsequent detection. For the commands, we construct a malicious shell command detector, which parsing the commands and employ a random forest classifier to achieve malicious detection. Then we also analyze the URLs for maliciousness to avoid identifying some normal external requests as the malicious ones. For the merged JS code, the first step is the obfuscation detection. Because the obfuscated packages often cannot detect by static analysis, we need to send them to dynamic detections module. Unobfuscated packages enter the static identifier, which is mainly implemented through static analysis and machine learning. Its main function is identify maliciousness, reduce the number of the packages entering the dynamic behavior extractor, and improve the overall detection efficiency. Then we use the GS instrument and Docker containers to extract an API sequence of obfuscated and suspicious packages, providing more detailed behavior information. Finally, we use a hierarchical classifier as the core to classify packages based on API sequences. Next is our evaluation section, which considers three main aspects: accuracy, efficiency, and validity. First, the dataset. We use several current datasets and harvest several blocks and the database of available malicious packages total more than 4,500. However, after manual check, we found the current dataset overlapped and some code was very similar, so we streamlined them. In addition, we also found that some packages has malicious code but cannot be exploited in real world. So we also include them and finally construct a dataset containing 1,159 malicious packages. Then we construct two benign datasets of 3,000 and 5,000 from the database of security packages and the NPM top popular 5,000 respectively. The first impairment, where we evaluate some subdetectors and DONAPI as a whole. Here we can see that they all show better result. Next, we test our hierarchical classifier and we can see that DONAPI achieve good recall on the main top four classes of malware packages. For M5, after analyzing the missing samples, we found that the unsatisfactory recall rate is mainly due to code obfuscation and incomplete behavior sequence. Therefore, we will improve the detector based on such samples. The second is an efficiency impairment that focuses on time overhead. To understand what's considered reasonable time overhead, we first count the number of packages updated daily in the NPM repository. The average is rough 16,000 per day and rough 220,000 per 2-week period. Next, we count the distribution of the detector's overhead for analysis packages. It can be seen that when we set the static analysis timeout to 300 seconds and the dynamic analysis timeout to 600 seconds can cover more than 90% of the packages. The reason why design such a timeout is also to reduce the impact of the individual complex and large packages on the overall analysis efficiency. Then we conduct an actual inspection of more than 15,000 packages updated between September 1st and 3rd, of which more than 4,000 enter the dynamic behavior extractor. In the end, a process took about 22 hours. At the rate, we estimate that our detector can analyze 17,000 packages in 24 hours, beating the 15 packages updated daily in the previous section. The third is the validity impairment, which is divided into two parts. First, we conduct a model comparison impairment on our dataset. Here we use and republicated some relatively works. They are AMFL from the University of South California, SAP from SAP Security Research, and GuardDog from Datadog Security Labs. As shown in table, We can see that our work has a low FP, which is crucial for large-scale detection. Next, we can see DONAPI have a more balanced performance on all metrics, being able to achieve over 90%. The graph below shows the model records of different types of malicious packages. As you can see, DONAPI have a relatively balanced performance on all categories of packages and have a clear advantages on M2, which is what differences from other tools. In addition to testing them on dataset, we also explore their efficiency in detecting packages in the wild. First, we deploy our tool on the server and run it continuously from January through May. Second, we detect all updates that we synchronized throughout May using the tool described in a previous section. DET in the table represents the number of detection, and the post-detection represents the number of real malicious samples in the detections. During our 5-month-long detection, we found a total 325 malicious packages in the wild, and 155 obfuscated suspicious packages that could not be identified as malicious. This proves DONAPI still has detection capability in real environments. Further, we can see that the other tools have more detections than DONAPI, but the post-detection is less. This shows the better robustness of DONAPI in the real world. Finally, to summarize our work. Thanks for listening.